Okay. So, we start the third module today, and this module will be mainly devoted to discussion on maxima minima for functions taking value in reals. I mean, to discuss about maxima minima, we need to compare the values of f defined on R n, and you can compare only if they are defined, their domain is R. So, let us start again with the motivation from function of one variable. So, let it be a differentiable function, differentiable on entire a b, open interval a b. So, you know that there is one beautiful theorem which is called Taylor's formula, and I mean one can motivate this maxima minima problem in many ways, but the explanation for this comes more beautifully if you understand the Taylor's formula. So, today let us concentrate on this pretty beautiful theorem which is called Taylor's formula. So, we will discuss a several variable part of it, but let us recall what it says. I told you in the beginning of while we were discussing about the motivation for differentiability, that suppose I have x naught a point and x naught and x 2 points in a b, maybe they are close to enough, then this f x. So, let us say there is x is in some interval x naught minus delta to x naught plus delta, then in this interval f x is kind of approximated, right, by f x f prime at x naught plus f at some point z x minus x naught. This is actually, if you say MVT, then you can write it as exactly this form, but if z and x naught are close enough, then you actually kind of approximate f x by this, right, z and x naught close enough. Close enough have to be again justified with delta and other things, and that comes in the statement of the theorem. We will do it, do not worry. But what it says that f is differentiable, then around x naught in some interval x naught, f x is kind of linearly approximated. This is a linear function, x going to f x naught plus f prime x naught x minus x naught, affine linear, this part is linear, yeah, this is a linear function. So, f x is linearly approximated around f x naught. Now, f is, suppose f is nice enough, f is more nice, in the sense that suppose f is n times differentiable, that is f prime n exists for 1 to n. Then this Taylor's formula tells you that f x is approximated around f x naught we have a better approximation. This is a first degree approximation, but here we can have a n degree approximation by a polynomial, and it is much better approximation than the error part here goes faster than error part here goes faster to 0 as x goes to x naught than here. And actually if you want to write exact expression, then I have to write here, replace here by some z in x to x naught. So, for closed n of x naught, this is so called Taylor's formula. And this part is called the remainder term, right. So, up to n minus 1 degree, fine, it is a all coefficient f prime x naught and a polynomial in x minus x naught, and the nth coefficient is z. So, the previous term here was f n minus 1 x naught x minus x naught power n minus 1 divided by n minus 1 factorial. And this gives to so called Taylor's series also, that if f is differentiable of all order, that is f n exists for all n, then to f x I can associate this series which goes on, and if you put conditions like for all f n in some for some delta f n x is bounded for all x in x naught minus delta to x naught plus delta, then see this series is actually converged to f x, and in that case we will write equal to. That is the Taylor's theorem. But in general, given f x which is differentiable of all order, we can associate this series, Taylor's series. It converges or not depends on certain nice condition like this, but this is one way to express. If it does, this is one way to f x as a power series expansion, so called real analytic function. So far so good for one variable. Now, how do you generalize it to f from u in R n to R m u open set? Now, how do you do it? Once again the idea is that, as you have done before, that f is from u to R m. So, you have m components. So, do it component wise. So, we will assume m to be 1, and if we can write down the generalized form of Taylor's formula here, we can write down for any f taking value in R m component wise. Well, to do this I have to talk about these higher derivatives. F prime, f double prime we have already discussed, but then we have to talk about nth derivatives. And as you have seen that even in the function for real variable, the second derivative is already a matrix. So, third derivative onwards you cannot write it so nicely, and to put, so what we try to do in mathematics, that if you cannot write things nicely, we try to take help of notation. So, we put some nice notation so that the final formula looks nice, but putting it in notation does not mean the calculation becomes easy. But anyway, to put it or to look it nicely, we fix up some notation. Well, so suppose I have a T n vector in Rn. So, this f prime at some x in Rn, x in U, x t, we just mean grad f x dot t. So, this is summation I equal to 1 to n del f del x I at x dot t I. Similarly, f double prime x, okay, capital T equal to, I write it in the summation form again and then you try to recognize what it is. Summation I equal to 1 to n, summation j equal to 1 to n, del square f del xi del xj, I am assuming everything exists of course, tj ti. This is notation for this thing, and if you recognize this is actually t prime Hessian of f, we have already introduced as xx t. Similarly, f 3 prime xt summation I equal to 1 to n, summation j equal to 1 to n, summation k equal to 1 to n, del cube f del x I xj xk tk tj ti, and if you want to write it in a compact, in a this more nicer looking form, this will be actually t prime h fx t dot t into, so this is scalar t ti. So, do not worry about this part. So, this more, it will become more and more difficult when you write for in general for any m or n. So, you can write it in the summation formula. Now, there is small hitch here that actually I have written I equal to 1 to n j to equal to x I x j t j t I, but here this is real numbers, all t and all t's are real numbers t i's. I could have written t I t j, here also I could have written t I t j t k, but I rewritten this order because when you talk about complex functions, then certain thing happens that you have to put bars complex conjugate. So, therefore, this is a standard notation that we can easily generalize to complex. Now, with this I can state the Taylor's formula for several variable which will of course match. So, I write this Taylor's formula in this notation. Okay. Here is a theorem. Let f from an open set U in Rn to R be such that all its partial derivatives exist up to order m, up to order say less than m and differentiable. So, partial derivative up to order m exist and they are also differentiable. I do not say f is differentiable up to order m or not. Partial derivative up to order less than m exist and also partial derivative of m them exist. Partial derivative of, so I can put it in one, maybe not to confuse you too much. Partial derivatives are differentiable. So, it is automatically assume they exist differentiable up to order less than m for some m. Let x and y be 2 points in U such that the line joining x y, we have used this notation before, this is set of all point T x plus 1 minus T y, T in 0 1, this is also in U. So, if you use a convex set, there is no problem here. Then there exists a z in the line x y such that f of y, let me write it in this form, f x equal to, how do you write it? Okay. F prime x at y minus x, I am following that rotation, half of y minus, half means 1 by 2 factorial, one by m minus 1 factorial plus f m z at, so this is the error term divided by m factorial. This is the generalization of Taylor's formula. So, written more compactly, this looks more nice, you will agree. So, this is the writing, this approximation part plus error part. Well, now if I prove it, I can prove the same proof will follow for n equal to 1, what we started with. And proof is again very easy. Proof is just using first variable for Taylor's formula, stress variable function. And we have already done it before in case of last week what we are doing, mean value theorem. So, let us see a quick proof here. As you can guess, I will start with U is an open set. So, what we will do? I will find a delta greater than 0 such that T x plus 1 minus T y, this belongs to U for all T in, this is again as I said to avoid the one sided derivativeness at the end point. So, here in x and y, since this line is there and there is a ball, I can also extend it here little bit, I can extend here it little bit, delta by and delta. So, I have extended this line, so that this line is there. So, little bit extended line will be also here because U is open. And we will look at the same kind of function here that we did for MBT. So, take GT equal to f of x plus t y minus x. Okay. Then f1 equal to g gfy, g1 equal to fy and g0 equal to f x, and as you can and you see 0 and 1 both are in this interval. So, I will apply the Taylor's formula for G. So, what I will apply? One variable Taylor's formula for G, and what we get? G1 minus G0 equal to summation k equal to 1 to m minus 1. If f is differentiable, this is a composition of two functions, f and a linear function. So, this is, so just observe g t is composition of two functions, f p t, where f is, as according to our assumption, u to r m r, and p t is simply x plus t y minus x. This is a linear function, so it is differentiable of all order, and f is assumed to be the all partial derivative are differentiable up to order less than m. So, G will have the same property by chain rule. So, I will write it was 1 by k factorial k derivative of G at some t naught at 0, 1 minus 0, okay, fine, 1 minus 0 is 1. So, I should have 1 minus 0 here, but 1 minus 0 is 1. So, this part plus the error part 1 by m factorial G prime t naught for some t naught in 0 to 1, correct. Now, what I have to do to get this formula, I have to see what are these fellows are. Well, let us see, just apply chain rule here. Well, what will happen? P is from R to Rn. So, P is can be written as P1, P2, Pn components, where each P I t. So, if my x is x1, x2, xn, y is y1, y2, yn, then each P I t is xi plus t yi minus xi. So, P I t, P I prime t is just yi minus xi. So, that will give me by chain rule G prime of t is how much? F prime P t, I am following that notation, at the derivative of P I, that is yi minus xi. Sorry. Oh, which is pi 1 notation f prime P t y minus x. Now, you apply G double prime t. This is what will be that? Again apply chain rule. Now, there will be summation I equal to 1 to n, j equal to 1 to n, del square f del xi del xj, f at pt yj minus xj yi minus xi. So, which is according to our notation is f double prime pt y minus x. So on you continue, you will see gmt equal to fm P t y minus x. Now, when I put it back, I will have g k at 0, and now observe P 0. So, can P t here, P 0 is simply, what is P? Yeah, P 0 is simply x. So, put it back, you will get the formula I written for Taylor's formula I written in the theorem. So, put them back all together. That is a straightforward proof of Taylor's formula. So, next time we will start from the Taylor's formula and talk about maximum minimum. Thank you.